So really the idea here is to set up the motivation behind BERT as an architecture and talk about some of the fundamental concepts underpinning it. I'm not trying to do too deep a dive into the actual application of BERT, but hopefully this frames why BERT was invented in the first place. We have a setup of word embedding, so typical methods from glove and word to vec, created static embedding. So no matter what context word was used, the pre-trained embedding would be identical, no matter what. But the hope is that these pre-trained embeddings, even if they are fixed, capture some notion of meaning or attributes about particular words. So again, we had this dementia example where in this case we had 300 dimensions. We're projecting into a 300-dimensional subspace. And the idea is that these 300 dimensions completely encapsulate all of these semantic and dependency meanings of the word dementia on average. So you are probably all familiar with vanilla neural networks. So again, just a refresher, each of these hidden units can be thought of as a neuron. It's essentially identical to a logistic classifier. The density of neural networks is stacking up multiple hidden units or logistic classifiers to model increasingly complex nonlinearities. So again, no sequential information. We get no context or meaning or sort of narrative across a sequence. And in the context of something like classifying dementia, there is going to be both local sequence information at the sentence level, and then also staging information on a larger time scale or units in years. So in order to leverage all of these different levels of granularity in terms of contextual relationships, we need an architecture that can account for connections that span more than a few dozen or 100 tokens. So the older solution was a recurrent neural network. So hopefully you guys have had some experience with recurrence as well. So recurrence is basically stacking many different nodes or neurons on top of each other and rolling them forward in time. So here are sequences, the patient has memory loss. And you can see that there's a hidden state corresponding to each time step, where each time step pertains to a given token. So if we're looking at the word patient, we're going to say, we're going to encode this into a vector xt, and then we would have ht as our hidden state pertaining to this word embedding. And this is going to get information from the prior token, the, in this case. So similarly for memory, it's going to get information from all of the previous tokens in terms of their hidden states. So the idea is that you can carry information along this chain. And if there's something that's relevant further down the chain, the neural network can pick up on the fact that certain tokens are related to each other via backpropagating through this recurrent neural network. So something like recurrence can accurately capture that memory is the thing being lost. It can also accurately capture that the patient is the agent losing their memory. So in this sense, what you gain with LSTM over a recurrent network is the ability to forget. So with a recurrent neural network, it's very difficult to say we no longer need to keep track of this piece of information or this facet of a word embedding. So this is useful for things like when has memory loss, which are these 3 tokens, come 100 words after the patient, which is a realistic example from an actual medical chart that I was working on. So there are 13 tokens in the setup, 512 dimensional embeddings, and 8 heads, 8 multiple attention heads. So you can see the multi-head function, which takes as input keys, queries, and value matrices, is going to be of dimension 13 by 512, because we have 13 tokens, and each is going to be embedded into a space of 512 dimensions. And this is going to be the product of the concatenation of each attention head and that final W0 weight matrix, or WO weight matrix. And so head 1 is going to be of dimension 13 by 64. And that's because, again, we have 13 tokens, and we've split our 512 dimensions into 8 different heads. So we have 64 dimensions per head. So you'll see the actual attention function here, which is, again, a function of keys, queries, and values, is equal to the softmax of the dot product of the keys and queries, as we talked about before, divided by the square root of the dimensionality. And this is what's called scaled dot product attention. This is the core attention model. So regardless of whether or not you're talking about BERT or you're talking about GPT-2 or a specific type of transformer or an application, the core attention model typically follows this design pattern, where you're going to have keys and queries. There's going to be a compatibility function that creates an energy score of some kind. You're going to turn those scores into a distribution, and then you're going to get attention weights as a result. So in our case, the compatibility function itself was the scaled dot product attention. So we chose to have that scaling factor. But there are many different compatibility functions that you could have used for this attentive relationship. So you're going to find in different use cases or different pieces of literature, people slightly modifying that scaled dot product attention, but they're all ways to measure some kind of compatibility. So if you see something other than scaled dot product attention, don't hesitate. It's just another form of compatibility. And that compatibility, the key is that it's some notion of compatibility between the keys and the queries. And then the distribution in our case was a softmax, and that's, I think, the most common example of what is a distribution function, but you might see something else that turns it into a distribution. Again, the idea is the same. You're trying to normalize it into some form of a distribution. The core output in a core attention model is always going to be this vector of attention weights that are used for some downstream purpose. And in our case of BERT, those attention weights get multiplied by the values, and that is taking a weighted average. So hopefully that still makes complete sense.